Clipping. Clipping is a graphics package allows the user to specify which part of a defined picture is to be displayed and where that part is to be placed on the display device. Any convenient Cartesian coordinate system, referred to as the World Coordinate Reference frame, can be used to define the picture. For a two-dimensional picture, a view is selected by specifying a sub-area of the total picture area. A user can select a single area for display, or several areas could be selected for simultaneous display or for an animated panning sequence across a scene. The picture parts with the selected areas are then mapped onto the specified areas of the device coordinates. When multiple view areas are selected, these areas can be placed in separate display locations, or some areas could be inserted into other larger display areas. Transformations from world to device coordinates involve translation, rotation, and scaling operations, as well as procedures for deleting those parts of the picture that are outside the limits of the selected display area. The viewing pipeline. A world coordinate area selected for display is called a window. An area on a display device to which a window is mapped is called a viewport. The window defines what is to be viewed. The viewport defines where it is to be displayed. Often, windows and viewports are rectangles in a standard position with the rectangle edges parallel to the coordinate axis. Other window or viewport geometries, such as general polygon shapes and circles, are used in some applications, but these shapes take longer to process. In general, the mapping of a part of a world coordinate scene to device coordinates is referred to as a viewing transformation. Sometimes the two-dimensional viewing transformation is simply referred to as a window to viewport transformation or the windowing transformation. But in general, viewing involves more than just the transformation from the window to the viewport. This figure illustrates the mapping of a picture section that falls within a rectangular window onto a designated rectangular viewport. A viewing transformation using standard rectangles for the window and viewport. In computer graphics terminology, the term window originally referred to an area of a picture that is selected for viewing, as defined at the beginning of this section. Unfortunately, the same term is now used in window manager systems to refer to any rectangular screen area that can be moved about, resized, and made active or inactive. In this chapter, we will only use the term window to refer to an area of the world coordinate scene that has been selected for display. Some graphics packages that provide window and viewport operations allow only standard rectangles, but a more general approach is to allow the rectangular window to have any orientation. In this case, we carry out the viewing transformation in several steps as indicated in this figure. The two-dimensional viewing transformation pipeline is shown in this figure. Next, to obtain a particular orientation for the window, we can set up a two-dimensional viewing coordinate system in the world coordinate plane and define a window in the viewing coordinate system. The viewing coordinate reference frame is used to provide a method for setting up arbitrary orientations for rectangular windows. Once a viewing reference frame is established, we can transform the descriptions in a world coordinates to viewing coordinates. We then define a viewpoint in normalized coordinates in the range from 0 to 1 and map the viewing coordinate description of the scene to normalized coordinates. At the final step, all parts of the picture that lie outside the viewport are clipped and the contents of the viewport are transferred to device coordinates. This figure illustrates a rotated viewing coordinate reference frame and the mapping to normalized coordinates. Setting up a rotated world window in viewing coordinates and the corresponding normalized coordinate viewport. By changing the position of the viewport, we can view objects at different positions on the display area of an output device. Also, by varying the size of viewports, we can change the size and proportions of displayed objects. We achieve zooming effects by successively mapping different size windows on a fixed size viewport. As the windows are made smaller, we zoom in on some part of a scene to view details that are not shown with larger windows. Similarly, more overview is obtained by zooming out from a section of a scene with successively larger windows. Panning effects are produced by moving a fixed size window across the various objects in a scene. Viewports are typically defined within the unit square normalized coordinates. This provides a means for separating the viewing and other transformations from specific output device requirements, so that the graphics package is largely device independent. Once the scene has been transferred to normalized coordinates, the unit square is simply mapped to the display area for the particular output device in use at that time. Different output devices can be used by providing the appropriate device drivers. When all coordinate transformations are completed, viewport clipping can be performed in normalized coordinates or in device coordinates. This allows us to reduce computations by concatenating the various transformation matrices. Clipping procedures are of fundamental importance in computer graphics. They are used not only in viewing transformations but also in window manager systems, in drawing packages to eliminate parts of a picture inside or outside of a designated screen area, and in many other applications. Viewing coordinate reference frame. This coordinate system provides a reference frame for specifying the world coordinate window. First, a viewing coordinate origin is selected at some world position P0 equals x0, y0. Then we need to establish the orientation or rotation of this reference frame. One way to do this is to specify a world vector v that defines the viewing yv direction. Vector v is called the view up vector. Given v, we can calculate the components of the unit vectors v equals vx, vy and u equals ux, uy for the viewing yv and xv axis, respectively. These unit vectors are used to form the first and second rows of the rotation matrix R that aligns the viewing xv, yv axis with the world xw, yw axis. We obtain the matrix for converting world coordinate position to viewing coordinates as a two-step composite transformation. Translate the viewing origin to the world origin. Rotate to align the two coordinate reference frames. The composite two-dimensional transformation to convert world coordinates to viewing coordinates is mwc.vc equals r and t, where t is the translation matrix that takes the viewing origin point P0 to the world origin, and R is the rotation matrix that aligns the axes of the two reference frames. This figure illustrates the steps in this coordinate transformation. This figure shows a viewing coordinate frame that is moved into coincidence with the world frame in two steps. A. Translate the viewing origin to the world origin, and then B. Rotate to align the axes of the two systems. Window to viewport coordinate transformation. Once object descriptions have been transferred to the viewing reference frame, we can choose the window extents in viewing coordinates and select the viewport limits in normalized coordinates. Object descriptions are then transferred to normalized device coordinates. We do this using a transformation that maintains same relative placement of objects in normalized space as they had in viewing coordinates. If a coordinate position is at the center of the viewing window, for instance, it will be displayed at the center of the viewport. This figure illustrates the window to viewport mapping. In this figure, a point at position xw, yw in a designated window is mapped to viewport coordinates xv, yv, so that the relative positions in these two areas are the same. A point at position xw, yw in the window is mapped onto position xv, yv in the associated viewport. To maintain the same relative placement in the viewport as in the window, we require that the following expressions be solved. Solving these expressions for the viewport position xv, yv, we have xv equals xv min plus xw minus xw min into sx. Likewise, yv equals yv min plus yw minus yw min into sy, where the scaling factors are Sx equals xv max minus xv min over xw max minus xw min. Sy equals yv max minus yv min over yw max minus yw min. Set of transformations that converts the window area into the viewport area. This conversion is performed with the following sequence of transformations. 1. Perform a scaling transformation using the fixed point positions of xw min, yw min that scales the window area to the size of the viewport. 2. Translate the scaled window area to the position of the viewport. Relative proportions of objects are maintained if the scaling factors are the same, Sx equals Sy. Otherwise, world objects will be stretched or contracted in either the x or the y direction when displayed on the output device. Character strings can be handled in two ways when they are mapped to a viewport. The simplest mapping maintains a constant character size even though the viewport area may be enlarged or reduced relative to the window. This method would be employed when text is formed with standard character fonts that cannot be changed. In systems that allow for changes in character size, string definitions can be windowed, the same as other primitives. For characters formed with line segments, the mapping to the viewport can be carried out as a sequence of line transformations. From normalized coordinates, object descriptions are mapped to the various display devices. Any number of output devices can be opened in a particular application, and another window-to-viewport transformation can be performed for each open output device. This mapping, called the workstation transformation, is accomplished by selecting a window area in normalized space and a viewport area in the coordinates of the display device. With the workstation transformation, we gain some additional control over the positioning of parts of a scene on individual output devices. As illustrated in this figure, we can use workstation transformations to partition a view so that different parts of normalized space can be displayed on different output devices. Figure shows mapping selected parts of a scene in normalized coordinates to different video monitors with workstation transformations. Two-dimensional viewing functions. We define a viewing reference system in a fixed application program with the following function. Evaluate view orientation matrix x0, y0, xv, yv, error, view matrix, where parameters x0 and y0 are the coordinates of the viewing origin and parameters xv and yv are the world coordinate positions for the view up vector. An integer error code is generated if the input parameters are in error. Otherwise, the view matrix for the world to viewing transformation is calculated. Any number of viewing transformation matrices can be defined in an application. To set up the elements of a window to viewport mapping matrix, we invoke the following function. Here, the window limits in viewing coordinates are chosen with parameters xwmin, xwmax, ywmin, ywmax, and the viewport limits are set with the normalized coordinate positions xvmin, xvmax, yvmin, and yvmax. As with the viewing transformation matrix, we can construct several window viewport pairs and use them for projecting various parts of the scene to different areas of the unit square. Next, we can store combinations of viewing and window viewport mappings for various workstations in a viewing table with the code shown here, where parameter ws designates the output device workstation and parameter view index sets an integer identifier for this particular window viewport pair. The matrices view matrix and view mapping matrix can be concatenated and referenced by the view index. Additional clipping limits can also be specified here, but they are usually set to coincide with the viewport boundaries. And parameter clip xy is assigned either the value noClip or the value clip. This allows us to turn off clipping if we want to view the parts of the scene outside the viewport. We can also select noClip to speed up processing when we know that all of the scene is included within the viewport limits. The function setViewIndex selects a particular set of options from the viewing table. This view index selection is then applied to subsequently specified output primitives and associated attributes and generates a display on each of the active workstations. At the fine stage, we apply a workstation transformation by selecting a workstation window viewport pair, as shown below, where parameter ws gives a workstation number. Window coordinate extents are specified in the range from 0 to 1, normalized space, and viewport limits are in integer device coordinates. If a workstation viewport is not specified, the unit square of the normalized reference frame is mapped onto the largest square area possible on an output device. The coordinate origin of normalized space is mapped to the origin of device coordinates, and the aspect ratio is retained by transforming the unit square onto a square area on the output device. Clipping operations. Any procedure that identifies those portions of a picture that are either inside or outside of a specified region or space is referred to as a clipping algorithm, or simply clipping. This region against which an object is to be clipped is called a clip window. Applications of clipping include extracting part of the defined scene for viewing, identifying visible surfaces in the three-dimensional views, anti-aliasing line segments or object boundaries, creating objects using solid modeling procedures, displaying a multi-window environment, and drawing and painting operations that allow parts of a picture to be selected for copying, moving, erasing, or duplicating. Depending on the application, the clip window can be a general polygon or it can even have curved boundaries. We first consider clipping methods using rectangular clip regions, then we discuss methods for other clip regions shapes. For the viewing transformation, we want to display only those picture parts that are within the window area, assuming that the clipping flags have not been set to no clip. Everything outside the window is discarded. Clipping algorithms can be applied in world coordinates so that only the contents of the window interior are mapped to device coordinates. Alternatively, the complete world coordinate picture can be mapped first to device coordinates or normalized device coordinates, then clipped against the viewport boundaries. World coordinate clipping removes those primitives outside the window from further consideration, thus eliminating the processing necessary to transform those primitives to device space. Viewport clipping, on the other hand, can reduce calculations by allowing concatenation of viewing and geometric transformation matrices. But viewport clipping does require that the transformation to device coordinates be performed for all objects, including those outside the window area. On raster systems, clipping algorithms are often combined with scan conversion. Algorithms for clipping: point clipping, line clipping, straight line segments, area clipping, polygons, curve clipping, text clipping. Line and polygon clipping routines are standard components of graphics packages, but many packages accommodate curved objects, particularly spline curves and conics, such as circles and ellipses. Another way to handle curved objects is to approximate them with straight line segments and apply the line or polygon clipping procedure. Point clipping. Assuming that the clip window is a rectangle in standard position, we save a point P equals x, y for display if the following inequalities are satisfied. xw_min is less than or equal to x, which is less than or equal to xw_max, and y lies between yw_min and yw_max, where the edges of the clip window xw_min, xw_max, yw_min, yw_max can be either the world coordinate window boundaries or viewport boundaries. If any one of these four inequalities is not satisfied, the point is clipped, not saved, for display. Although point clipping is applied less often than the line or polygon clipping, some applications may require a point clipping procedure. For example, point clipping can be applied to scenes involving explosions or sea foam that are modeled with particles, points, distributed in some region of the scene. Line clipping. The following figure illustrates possible relationships between line positions and a standard rectangular clipping region. A line clipping procedure involves several parts. First, we can test a given line segment to determine whether it lies completely inside the clipping window. If it does not, we try to determine whether it lies completely outside the window. Finally, if we cannot identify a line as completely inside or completely outside, we must perform intersection calculations with one or more clipping boundaries. We process lines through the inside-outside test by checking the line endpoints. A line with both endpoints inside all clipping boundaries, such as the line from P1 to P2, is saved. A line with both endpoints outside any one of the clip boundaries, line P3, P4, in the previous figure, is outside the window. All of the lines cross one or more clipping boundaries and may require calculation of multiple intersection points. To minimize calculations, we try to devise clipping algorithms that can efficiently identify outside lines and reduce intersection calculations. For a line segment with endpoints x1, y1 and x2, y2, and one or both endpoints outside the clipping rectangle, the parametric representation x equals x1 plus u into x2 minus x1 and y equals y1 plus u into y2 minus y1, with lying between 0, u and 1, could be used to determine values of parameter u for intersections with the clipping boundary coordinates. If the value of u for an intersection with rectangular boundary edge is outside the range 0 to 1, the line does not enter the interior of the window at that boundary. If the value of u is within the range from 0 to 1, the line segment does indeed cross into the clipping area. This method can be applied to each clipping boundary edge in turn to determine whether any part of the line segment is to be displayed. Line segments that are parallel to window edges can be handled as special cases. Clipping line segments with these parametric tests require a good deal of computation, and faster approaches to clipping are possible. Some line clipping algorithms are Cohen-Sutherland line clipping, Liang-Baske line clipping. This is one of the oldest and most popular line clipping procedures. Generally, the method speeds up the processing of line segments by performing initial tests that reduce the number of intersections that must be calculated. Every line endpoint in a picture is assigned a 4-digit binary code called a region code that identifies a location of the point relative to the boundaries of the clipping rectangle. Regions are set up in reference to the boundaries as shown in this figure. Binary region codes assigned to line endpoints according to the relative position with respect to the clipping rectangle. Each bit position in the region code is used to indicate one of the 4 relative coordinate positions of the point with respect to the clip window, to the left, right, top, or bottom. By numbering the bit positions in the region code as 1 through 4 from right to left, the coordinate regions can be correlated with the bit positions as bit 1 left, bit 2 right, bit 3 below, bit 4 above. A value of 1 in any bit position indicates that the point is in that relative position. Otherwise, the bit position is set to 0. If a point is within the clipping rectangle, the region code is 0, 0, 0, 0. A point that is below and to the left of the rectangle has a region code of 0, 1, 0, 1. Bit values in the region code are determined by comparing endpoint coordinate values x, y to the clip boundaries. Bit 1 is set to 1 if x is less than xw min. The other 3 bit values can be determined using similar comparisons. For languages in which bit manipulation is possible, region code bit values can be determined with the following 2 steps. 1. Calculate differences between endpoint coordinates and clipping boundaries. 2. Use the resultant sign bit of each difference calculation to set the corresponding value in the region code. Bit 1 is in the sign bit of x minus xw min, but bit 2 is in the sign bit of xw max minus x. Bit 3 is in the sign bit of y minus yw min, and bit 4 is in the sign bit of yw max minus y. Once we have established region codes for all line endpoints, we can quickly determine which lines are completely inside the clip window and which are clearly outside. Any lines that are completely contained within the window boundaries have a region code of 0, 0, 0, 0 for both endpoints, and we trivially accept these lines. Any lines that have a 1 in the same bit position in the region codes for each endpoint are completely outside the clipping rectangle, and we trivially reject these lines. We would discard the lines that has a region code of 1, 0, 0, 1 for one endpoint and a code of 0, 1, 0, 1 for the other endpoint. Both endpoints of this line are left of the clipping rectangle, as indicated by the 1 in the first bit position of each region code. A method can be used to test lines for total clipping is to perform the logical and operation with both region codes. If the result is not 0000, the line is completely outside the clipping region. Lines that cannot be identified as completely inside or completely outside a clip window by these tests are checked for intersection with the window boundaries. As shown in this figure, such lines may or may not cross the window interior. This figure shows that lines extending from one coordinate region to another may pass through the clip window, or they may intersect clipping boundaries without entering the window. We begin the clipping process for a line by comparing an outside endpoint to a clipping boundary to determine how much of the line can be discarded. Then the remaining part of the line is checked against the other boundaries, and we continue until either the line is totally discarded or a section is found inside the window. Set up our algorithm to check endpoints against clipping boundaries in the order left, right, bottom, top. To illustrate the specific steps in clipping lines against rectangular boundaries using the Cohen-Sutherland algorithm is shown in the given figure. Starting with the bottom end point of the line from P1 to P2, we check P1 against the left, right, and bottom boundaries in turn and find that this point is below the clipping rectangle. We then find the intersection point P1' with the bottom boundary and discard the line section from P1 to P1'. The line has now been reduced to the section P1' to P2. Since P2 is outside the clip window, we check this endpoint against the boundaries and find that it is to the left of the window. Intersection point P2' is calculated, but this point is above the window. So the final intersection calculation yields P2 double dash and the line from P1' to P2 double dash is saved. This completes processing for this line, so we save this part and go on to the next line. Point P3 in the next line is to the left of the clipping rectangle, so we determine the intersection P3' and eliminate the line section from P3 to P3'. By checking region codes for the line section from P3' to P4, we find that the remainder of the line is below the clip window and can be discarded also. Intersection points with the clipping boundary can be calculated using the slope-intercept form of the line equation. For a line with endpoint coordinates x1, y1 and x2, y2, the y-coordinates of the intersection point with the vertical boundary can be obtained with the calculation y equals y1 plus m into x minus x1, where the x value is set either to xw min or to xw max, and the slope of the line is calculated as m equals y2 minus y1 over x2 minus x1. Similarly, if we are looking for the intersection with the horizontal boundary, the x-coordinate can be calculated as x equals x1 plus y minus y1 over m, with y set either to yw min or yw max. The following procedure demonstrates the Cohen-Sutherland line clipping algorithm. Codes for each endpoint are stored as bytes and processed using bit manipulations. Liang-Barsky line clipping. Faster line clippers have been developed that are based on analysis of the parametric equation of a line segment, which we can write in the form x equals x1 plus u delta x, y equals y1 plus u delta y, where u lies between 0 and 1, where delta x equals x2 minus x1 and delta y equals y2 minus y1. Later, Liang and Barsky independently devised an even faster parametric line clipping algorithm. Following the Liang-Barsky approach, we first write the point clipping conditions in parametric form, as shown below. Each of these four inequalities can be expressed as U pk less than or equal to qk, where k equals 1, 2, 3, and 4, where parameters p and q are defined as shown here. Any line that is parallel to one of the clipping boundaries has pk equals 0 for the value of k corresponding to the boundary k equals 1, 2, 3, and 4 correspond to the left, right, bottom, and top boundaries respectively. If for that value of k we also find qk is less than 0, then the line is completely outside the boundary and can be eliminated from further consideration. If qk is greater or equal to 0, the line is inside the parallel clipping boundary. When pk is less than 0, the infinite extension of the line proceeds from the outside to the inside of the infinite extension of this particular clipping boundary. If pk is greater than 0, the line proceeds from inside to the outside. For a non-zero value of pk, we can calculate the value of u that corresponds to the point where the infinitely extended line intersects the extension of boundary k as u equals qk by pk. For each line, we can calculate values for parameters u1 and u2 that define that part of the line that lies within the clip rectangle. The value of u1 is determined by looking at the rectangle edges for which the line proceeds from the outside to the inside. P is less than 0. For these edges, we calculate rk equals qk by pk. The value of u1 is taken as the largest of the set consisting of 0 and the various values of r. Conversely, the value of u2 is determined by examining the boundaries for which the line proceeds from inside to outside. P is greater than 0. A value of rk is calculated for each of these boundaries, and the value of u2 is the minimum of the set consisting of 1 and the calculated r values. If u1 is greater than u2, the line is completely outside the clip window and it can be rejected. Otherwise, the endpoints of the clipped line are calculated from the two values of the parameter u. This algorithm is presented in the following procedure. Line intersection parameters are initialized to the values of u1 equals 0 and u2 equals 1. For each clipping boundary, the appropriate values for p and q are calculated and used by the function clipTest to determine whether the line can be rejected or whether the intersection parameters are to be adjusted. When p is less than 0, the parameter r is used to update u1. When p is greater than 0, parameter r is used to update u2. If updating u1 or u2 results in u1 being greater than u2, we reject the line. Otherwise, we update the appropriate u parameter only if the new value results in a shortening of the line. When p equals 0 and q is less than 0, we can discard the line since it's parallel to and outside of this boundary. If the line has not been rejected, after all four values of p and q have been tested, the endpoints of the clipped line are determined from values u1 and u2. The pseudocode for Liang-Baszke algorithm is presented below. In general, the Liang-Baszke algorithm is more efficient than the Cohen-Sutherland algorithm since intersection calculations are reduced. Each update of parameters u1 and u2 requires only one division, and window intersections of the line are computed only once when the final values of u1 and u2 have been computed. In contrast, the Cohen-Sutherland algorithm can repeatedly calculate intersections along a line path even though the line may be completely outside the clip window. And each intersection calculation requires both a division and a multiplication. Both the Cohen-Sutherland and the Liang-Baszke algorithms can be extended to three-dimensional clipping. Solved example. Problem: use the Liang-Baszke algorithm to clip the lines in this figure. Solution: for line AB we have the following parameters. Since P2 equals 0 and Q2 is less than -2, AB is completely outside the right boundary. For line CD, we have the following parameters. Thus, U1 equals max of 0, minus 5 by 3 equals 0, and U2 equals minimum of 1 and 1 by 3 equals 1 by 3. Since U1 is less than U2, the two endpoints of the clipped line are 3, 7 and 3, 7 plus 3 into 1 by 3 equaling 3.8. For line EF, we have the following parameters. Thus, U1 equals max of 0, minus 1 by 6, minus 1 equaling 0, and U2 equals minimum of 1, 7 by 6, 5 equaling 1. Since U1 is 0 and U2 equals 1, the line EF is completely inside the clipping window. For line GH, we have the following parameters. Thus, U1 equals max of 0, minus 5 by 2, minus 4 by 3 equals 0, and U2 equals minimum of 1, 3 by 2, 2 by 3 equaling 2 by 3. Since U1 is less than U2, the two endpoints of the clipped line are 6, 6 and 6 plus 2 into 2 by 3 plus 6 plus 3 into 2 by 3 equaling 7 into 1 by 3, 8. For line IJ, we have the following parameters. Thus, U1 equals max of 0, 1 by 6, minus 1 by 6 equaling 1 by 6, and U2 is the minimum of 1, 5 by 6, 5 by 6 equaling 5 by 6. Since U1 is less than U2, the two endpoints of the clipped line are minus 1 plus 12 into 1 by 6, 7 plus minus 6 into 1 by 6, and minus 1 plus 12 into 5 by 6, 7 plus minus 6 into 5 by 6 equaling 9, 2. Cyrus-Beck parametric line clipping algorithm. This algorithm is more efficient than the Cohen-Sutherland algorithm. It employs parametric line representation and simple dot products. Parametric equation of line P0 P1 is P of t equals P0 plus t into P1 minus P0. Let Ni be the outward normal edge EI. Now pick any arbitrary point PEI on edge EI, then the dot product Ni into Pt minus PEI determines whether the point Pt is inside the clip edge or outside the clip edge or on the clip edge. The point P of t is inside if Ni dot P of t minus PEI is less than 0. The point P of t is outside if Ni dot P of t minus PEI is greater than 0. The point P of t is on the edge if Ni dot P of t minus PEI is equal to 0, intersection point. Now we can solve for the value of t at the intersection of P0 P1 with the edge Ni dot P of t minus P of EI minus PEI equals 0. First substitute for P of t, replacing P of t with P0 plus t into P1 minus P0. Ni into P0 plus t of P1 minus P0 minus PEI equals 0. Next, group terms and distribute the dot product. Ni into P0 minus PEI plus Ni into t into P1 minus P0 equals 0. Let d equals P1 minus P0 be the vector from P0 to P1 and solve for t. T equals Ni into P0 minus PEI over minus Ni into D. It is valid for the following conditions. Ni not equals 0, error cannot happen. D not equal to 0, P1 is not equal to P0. Ni into D not equal to 0, P0, P1 is not parallel to EI. Example of Cyrus-Beck algorithm. Compute T for each clip rectangle edge. Discard values of T outside. 0, 1. They are not on line segment TR, TB, TR. Classify other candidates more carefully. TL. Cyrus-Beck classifying intersections. Potentially entering intersection PE. Ni into D less than 0, angle greater than 90 degrees implies TL. Potentially leaving intersection PL. Ni dot D is greater than 0, angle less than 90 degrees implies TT. Comparison between Liang-Bursky and Cyrus-Beck parametric algorithms is shown in this table. Polygon clipping. A polygon boundary processed with the line clipper may be displayed as a series of unconnected line segments as shown on this figure, depending on the orientation of the polygon to the clipping window. What we really want to display is a bounded area after clipping as shown in this figure. For polygon clipping, we require an algorithm that will generate one or more closed areas that are then scan converted for the appropriate area fill. The output of a polygon clipper should be a sequence of vertices that defines the clipped polygon boundaries. Sutherland-Hodgman polygon clipping. We can correctly clip a polygon by processing the polygon boundary as a whole against each window edge. This could be accomplished by processing all polygon vertices against each clip rectangle boundary in turn. Beginning with the initial set of polygon vertices, we could first clip the polygon against the left rectangle boundary to produce a new sequence of vertices. The new set of vertices could then be successively passed to a right boundary clipper, a bottom boundary clipper, and a top boundary clipper as shown in this figure. At each step, a new sequence of output vertices is generated and passed to the next window boundary clipper. There are 4 possible cases when processing vertices in sequence around the perimeter of a polygon. As each pair of adjacent polygon vertices is passed to a window boundary clipper, we make the following tests. If the first vertex is outside the window boundary and the second vertex is inside, both the intersection point of the polygon edge with the window boundary and the second vertex are added to the output vertex list. If both input vertices are inside the window boundary, only the second vertex is added to the output vertex list. If the first vertex inside the window boundary and the second vertex is outside, only the edge intersection with the window boundary is added to the output vertex list. If both the input vertices are outside the window boundary, nothing is added to the output list. These 4 cases are illustrated in this figure for successive pairs of polygon vertices. Once all vertices have been processed for one clip window boundary, the output list of vertices is clipped against the next window boundary. We illustrate this method by processing the area in this figure against the left window boundary. Vertices 1 and 2 are found to be on the outside of the boundary. Moving along to vertex 3, which is inside, we calculate the intersection and save both the intersection point and vertex 3. Vertices 4 and 5 are determined to be inside, and they also are saved. The 6th and final vertex is outside, so we find and save the intersection point. Using the 5 saved points, we would repeat the process for the next window boundary. Implementing the algorithm as we have just described requires setting up storage for an output list of vertices as a polygon is clipped against each window boundary. We can eliminate the intermediate output vertex lists by simply clipping individual vertices at each step and passing the clipped vertices onto the next boundary clipper. This can be done with parallel processes or a single processor and a pipeline of clipping routines. A point, either an input vertex or a calculated intersect point, is added to the output vertex list only after it has been determined to be inside or on a window boundary by all 4 boundary clippers. Otherwise, the point does not continue in the pipeline. This figure shows a polygon and its intersection points with a clip window. In this figure, we illustrate the progression of the polygon vertices through a pipeline of boundary clippers. The following procedure demonstrates the pipeline clipping approach. An array S records the most recent point that was clipped for each clip window boundary. The main routine passes each vertex P to the clip point routine for clipping against the first window boundary. If the line defined by endpoints P and S boundary crosses this window boundary, then the intersection is calculated and passed to the next clipping stage. If P is inside the window, it is passed to the next clipping stage. Any point that survives clipping against all window boundaries is then entered into the output array of points. The array first point stores for each window boundary the first point clipped against that boundary. After all polygon vertices have been processed, a closing routine clips lines defined by the first and last points clipped against each boundary. The Sutherland-Hodgman polygon clipping algorithm is now shown on the screen. Convex polygons are correctly clipped by the Sutherland-Hodgman algorithm, but concave polygons may be displayed with extraneous lines as demonstrated in this figure. This occurs when the clipped polygon should have 2 or more separate sections, but since there is only one output vertex list, the last vertex in the list is always joined to the first vertex. There are several things we could do to correctly display concave polygons. For one, we could split the concave polygon into 2 or more convex polygons and process each convex polygon separately. Another possibility is to modify the Sutherland-Hodgman approach to check the final vertex list for multiple vertex points along any clip window boundary and correctly join pairs of vertices. Finally, we could use a more general polygon clipper such as the Weiler-Atherton algorithm. Weiler-Atherton polygon clipping. Here the vertex processing procedures for window boundaries are modified so that the concave polygons are displayed correctly. This clipping procedure was developed as a method for identifying visible surfaces, and so it can be applied with arbitrary polygon clipping regions. The basic idea in this algorithm is that instead always of proceeding around the polygon edges as vertices are processed, we sometimes want to follow the window boundaries. Which path we follow depends on the polygon processing direction, clockwise or counterclockwise, and whether tile pair of polygon vertices currently being processed represents an outside to inside pair or an inside to outside pair. For clockwise processing of polygon vertices, we use the following rules. For an outside to inside pair of vertices, follow the polygon boundary. For an inside to outside pair of vertices, follow the window boundary in a clockwise direction. In this figure, the processing direction in the Weiler-Atherton algorithm and the resulting clipped polygon is shown for a rectangular clipping window. An improvement on the Weiler-Atherton algorithm is the Weiler algorithm, which applied constructive solid geometry ideas to clip an arbitrary polygon against any polygon clipping region. This figure illustrates the general idea in this approach. For the two polygons, the correctly clipped polygon is calculated as the intersection of the clipping polygon and the polygon object. Other polygon clipping algorithms. The various parametric line clipping methods have also been adapted to polygon clipping, and they are particularly well suited for clipping against convex polygon clipping windows. The Liang-Barsky line clipper, for example, can be extended to polygon clipping with a general approach similar to that of the Sutherland-Hodgman method. Parametric line representations are used to process polygon edges in order around the polygon perimeter using region testing procedures similar to those used in line clipping. Text clipping. There are several techniques that can be used to provide text clipping in a graphics package. The clipping technique used will depend on the methods used to generate characters and the requirements of a particular application. The simplest method for processing character strings relative to the window boundary is to use the all or none string clipping strategy shown in this figure. Figure shows text clipping using a bounding rectangle about the entire string. If all the string is inside a clip window, we keep it. Otherwise, the string is discarded. This procedure is implemented by considering a boundary rectangle around the text pattern. The boundary positions of the rectangle are then compared to the window boundaries, and the string is rejected if there is any overlap. This method produces the fastest text clipping. An alternative to rejecting an entire character string that overlaps a window boundary is to use the all or none character clipping strategy. Here we discard only those characters that are not completely inside the window. See figure. In this case, the boundary limits of individual characters are compared to the window. Any character that either overlaps or is outside a window boundary is clipped. A final method for handling text clipping is to clip the components of individual characters. We now treat characters in much the same way that we treated lines. When an individual character overlaps a clip window boundary, we clip off the parts of the character that are outside the window. See figure. Outline character fonts formed with line segments can be processed in this way using a line clipping algorithm. Characters defined with bitmaps would be clipped by comparing the relative position of the individual pixels